Good afternoon. My name is Rui Carvalho, and I'm from Plastics 4B. And we're developing materials to build scaffolds, which will be used to grow tissues for medical applications. But to bring a bit of context, I'll first talk about organ failure. By some reason, either accidents, traumas, injuries, sometimes our organs get damaged, and you need to replace them. Currently, we can rely temporarily on artificial organs, but most of the time, we end up relying on transplants from a compatible donor. The problem with these options is that our body recognizes these as foreign objects and will reject them. So, to counter that, we use drugs that need to be taken for life that lower our immune system and make us more prone to infections and diseases. While thinking of alternatives, scientists remembered about stem cells, which were discovered 60 years ago. These self-replicating cells can differentiate and can transform into various types of tissues. So once human stem cells were first grown in a lab just 20 years ago, scientists jumped onto an idea of using these cells to grow tissues to repair our organs and ultimately create organs to replace our own. And just to show how interested they are, there are currently over 30 stem cell improvements pending FDA approval. But to build a tissue, you need more than stem cells. You also need scaffolds. That's because shape is essential to a function. So to build a working tissue, you need to set a template, that's what the scaffold does, where the cells grow with the correct three-dimensional shape they need. And after the process, it takes about 2-3 months to most tissues is complete, the scaffolds must degrade. Otherwise, they would interfere with the tissue. The problem with the current scaffolds is that they lower cell viability. We get more dead cells. Cell replication is also slower. And sometimes, we get some cells that change into tissues that we do not want. And why does this happen? Because of the materials they use. They sometimes release acidic degradation products, and high acidity causes cell inflammation. They promote low cell adhesion and take sometimes too long to degrade compared to the applications we're studying. So we need better materials and ones who can tune to the tissue at hand. And that's where we come in. We are experts in enzymatic technology, and for the past decade, we have been working on our proprietary process that uses enzymes through a clean process that uses no toxic solvents to produce many types of products. And we discovered that with very specific building blocks, monomers, we could create these chains, these polymers, that no one had ever synthesized before and had very good properties for tissue engineering. And our platform was flexible enough so we can add other building blocks, introduce modifications to our polymers, and fine-tune them to the various types of tissues. This is the heart of our project. We're now currently we're patenting the process and the products. The product we're selling, which are called scaffolds 4B, is a polymeric material which releases degradation products with low acidity, making it more compatible with living tissues, promotes high cell adhesion, which facilitates cell growth, and degrades quickly. We'll be selling this in powder or a filament form to R&D groups, and it's they who are going to then use melt and mold methods to turn them into the shapes they need for their research. But for melting, they need low melting points because processing polymers at high temperatures means they will break down. We got that covered. Our melting point is low. We're also better at promoting cell replication and growth than most of our major competing materials, and our degradation time is only a couple of months. The global market for these types of polymers to use in biomedical applications is growing at 14% per year, and is expected to reach above $2 billion by 2025. Most of it will be in the sectors of drug delivery and orthopedics. Now, we're looking first at USA and Europe, since it's where the most healthcare expenses by GDP are, and they together make about 60% of the market. Since we need regulatory approval to get into the market, with just getting these two approvals, we can reach a large part of the global market. Our entry point will be the stem cell tissue engineering, but we plan on developing products to reach the other sectors. As a company, we'll be focusing on R&D and tailoring these polymers, designing them to be used for specific tissues. Our production itself, large scale, will be outsourced. We'll engage our customers by first providing them free sampling, and in return, we get validation of our results, and we gain scientific recognition, which will help our sales. These sales will be made either through direct or through distributors who will help us reach a broader base of customers. Revenue model will be simple. We'll be selling a product as per unit, per weight unit. To get to the market, it should be approximately 3 years. We still need some more R&D and go through several upscale stages. We also need to get regulatory approval, and for that, we're going to need 2.8 million euros. This is expected to be paid back in our 2nd year of sales, and by our 5th year, we expect to have revenues above $50 million. Our continuous R&D will be used to develop more products to tap into the other markets, the orthopedics and drug delivery, and with that, we can increase our revenue sources. The team that's carrying this is composed by researchers with our help from a management student and has been greatly helped by our HiTech mentors. And this is where I want to be, to help build the bridge between stem cells and tissues and organs. Thank you very much for your attention.